All right, everyone. Today is the last day of class. Let me share my screen with you. For today's class, we'll be finishing up the lecture on the chi-square distribution, and I will show you examples of how to use the chi-square distribution in JASP in order to solve the sort of problems, the goodness of fit, and comparing two samples. And we'll also look at another implementation of the JASP software to analyze first an independent samples t-test example, and then a correlation prediction example. And I will use these demos. I will give you a sort of step-by-step demo, and there will be a very, very short homework assignment where for one of each of these types, you'll sort of look at a new data set, and by following along with my tutorial, you can answer some basic questions about that. And that will be the final graded homework assignment. And there will also be an extra credit component of that one for those of you who would like another bit of credit in addition to the homework assignment extra credit that I've already assigned. So just to review, there is not going to be an in-class final. The final will be like the previous quiz where I post an assignment on Blackboard called Quiz 4, and it will be posted on the first day of the final exam period, and then it will be posted on the first day of the final exam period, and then it'll be due on the last day of final exams, but not on the absolute last moment, like 11:59 p.m. It'll instead be due at noon, which will give me time to grade it. All right, now time to share my screen with y'all. All right, do you guys see my screen okay?
Yep.
Very good. All right, so where last we left off, we were talking about the chi-square distribution for a very, very simple kind of data set. So to give an example, you have one set of scores. You have a set of scores on a particular variable, and then there are two different types of, the scores can be one of several different types of groups or different types of conditions. So for example, last time we talked about a study where you, the experimenter, were interested in classifying the gender of characters that appear on cereal boxes. I looked this up after our last study, and this study, Black et al. 2009, is apparently an incredibly highly cited study that looks at Australian cereal boxes and was actually used to, like, as the basis of legislation in Australia to kind of create gender equity in the representation of characters on cereal boxes and other kinds of media directed at children. And like children's cereal boxes are considered media directed primarily at children because children are often the ones who want to buy sugary types of cereal. So it's just an interesting bit of example of a statistical study that was used to inform actual public policy. So in this study, the experimenters looked at like about 1,200 cereal boxes and wrote down the number of cereal boxes that have male and female characters. They found that in their sample of cereal boxes, 996 of the cereal boxes contained a representation of a male character, and 390 contained a representation of a female character. If you were to have this as a spreadsheet, which I'll show you in a second example of, not with 1,200 cases, but with much fewer, you would have cases, so rows in the spreadsheet, where one of the columns is going to be, there's going to be one column, and it's just going to say male. There's only one type of data, one type of variable here, and it's the gender. So this is a difference from, I believe, all of the other kinds of statistical tests we've studied so far, where there were always at least two variables. So in the case of the independent samples t-test, there was group as a variable, and there was also the score associated with each participant in each group. With the correlation and prediction, there were two numeric variables that were correlated with each other, or we were predicting one based on the other. But here, there's only one variable, and that variable is going to be the only variable for each of the cases. So if there are about 1,200 serial boxes, there'll be 1,200 scores total. So to go back to the serial box example, there's two different kinds of information that we need in order to figure out whether the observations on the distribution of male and female characters on serial boxes is sufficiently surprising given our expectations about what we think the distribution would be given certain assumptions. So in this case, there was an overrepresentation of male as opposed to female characters on serial boxes. There was nearly 3 times as many male characters. And for the sake of this study, they chose as the expected frequency of the presence of males and females on serial boxes that you would expect an equal number of male characters and female characters to appear on serial boxes. Now this expected frequency, where it's just you expect a 50-50 split if you have 2 different variables, this is something where it's often a matter of interpretation what the expected frequency should be. So expected is like the word expectation, and expectations are often a matter of opinion and interpretation. And we'll see examples of how the surprisingness of a finding can be very different depending on what our expectations going into the data are. So what you see here is a little bit of an overview of the kind of math that is done to figure out the test statistic called chi-squared for the chi-squared test. So you first calculate the difference between the observation of each variable and the expected observations, in this case, assuming a 50-50 split between male and female characters. And here, when you have 2 variables and you expect a 50-50 split, the differences are going to be, one is going to be positive, one is going to be negative. And then just like before, there's often a step in these problems where we take the squared difference. And then there's a second step where we take the squared difference, but then we weight it, as it's called, by our expectations about the frequency. And that gives us, in this case, 2 numbers for our 2 variables. And here, they're both the same. And this is just something that only happens when you have 2 variables and you expect an equal distribution of both. If you have more than 3 variables, you would expect different numbers here. But if you want to calculate chi-square, the test statistic for our problem, it's simply a matter of taking the sum of this squared difference weighted by expected frequency. So the chi-square statistic for the data from Black et al. 2009 is 132.48 plus the same number. And here is an example of, before we get to that, let's consider what the comparison distribution will be. So the comparison distribution is going to be what's called the chi-square distribution. Makes sense because the statistic that we're going to be testing is also called chi-square, so it makes sense that we would be locating a test statistic called chi-square on a distribution of chi-square scores. And like the t-distribution, the chi-square distribution differs depending on how many degrees of freedom your study has. And the degrees of freedom your study has is pretty simple. It's the number of categories your variable has. Well, that's simply all you need to know. The degrees of freedom is the number of categories your variable has minus 1. And for this kind of problem, you need at least 2 different categories, like male and female. That's the minimum number of categories, because otherwise every score could only have 1 value and there'd be nothing to test. So the degrees of freedom is always going to be at least 1, and it can go up arbitrarily, but typically the number of categories you have will be between like 2 and maybe 20. So here, our degrees of freedom is the number of categories, 2 minus 1. So we have 1 degree of freedom. And there's a Shiny app for figuring out what the chi-square distribution you're working with will be. And also, you need to know the alpha value, just like for all the other tests we've done. And that will determine where the cutoff is for the particular chi-square distribution you're working with. So let me quickly open that up and we can look at this together. So now I'm just going to go switch from sharing the PowerPoint itself to sharing my screen so we can look at Chrome together. All right, so can all of you see the chi-square distribution on my screen?
Yeah.
All right, very good. So the chi-square distribution is in many ways the simplest kind of distribution there is, because there's very, very little to understand and you don't need to deal with figuring out the kind of tail test, because there's only one possible tail test that you can do. So just like before, we have a left panel that gives us options. For this first part, we're going to just do the adjust probability option. That's what we use when we're trying to find the cutoff. The degrees of freedom, just like for the t distribution, we can choose any number we want, but in our case, it's going to be 1. And here we can choose the upper tail probability, which is the same as that alpha value. You can choose between the little slider or the number entry box. Number entry box is useful because you just see the number right there. So for this problem, assuming an alpha value of 0.05 and 1 degree of freedom, this chi-square distribution will have a cutoff value of 3.84. And everything above, any test statistic, any chi-square of your study above 3.84 would cause you to reject the null hypothesis. And when you reject the null hypothesis, we'll get to this in just a second, but about what the interpretation is. But when you reject the null hypothesis for a chi-square distribution, the interpretation is that your findings, your observed findings, deviate from your expected findings, which is to say, your actual observations are surprising in light of your expectations about what the distribution of the different what the distribution of the data would be with different assumptions. So in terms of the chi-square degrees of freedom, as you can see, when you go from 1 degree of freedom to 2 to 4 to higher, it looks like a distribution that sort of is shifting to the right. And before I go back to the chi-square distribution, what do you assume will happen to the cutoff chi-square as you go higher in degrees of freedom? So another way to put this is, if you have 3 categories instead of 2 categories in your chi-square distribution, so your degrees of freedom go from 1 to 2, do you think that will cause the cutoff to increase or decrease? Just think about it in your head, but let's try going from 1 degree of freedom to 2. So when we were at 1, the cutoff was 3.84, and now with 2 degrees of freedom, the cutoff is 5.99. And as you know, when you increase the cutoff score, it becomes more difficult to reject the null hypothesis. And if you increase the degrees of freedom from 2 to 3, it goes from 5.99 to 7.81. And we'll get to it in just a second. We'll explain why this happens. But you can think of it along the lines of, as you create a study where there's more than 3 categories, and you're expecting like a certain distribution of 3 categories, it's sort of easier just through random sampling to get an uneven distribution of 3 categories than it is to get an uneven distribution of 2 categories. Yeah, you'll see an example of that in just a moment. But there is like an intuitive explanation that I think is useful, even though you can toggle it yourself with the Shiny app. So here is an example of our samples chi-square score, which is our test statistic, and our chi-square distribution, that is our comparison distribution. And just like we saw on the Shiny app, the cutoff for the chi-square critical value was about 3.84, and everything to the right of that on the distribution is in that critical region where if our sample statistic falls there, that would cause us to reject the null hypothesis. But here, just like we pointed out last time, the sample chi-square score is 264, and the cutoff was 3.84. In a certain sense, it's kind of overkill. Like, look how unlikely, look how far away from the cutoff value our sample was. And you might think, well, this is like very strange in light of the other statistical tests we've done previously, where even a very, very extreme difference between 2 groups in independent samples t-test problem would not result in a sample t-score that's so far away from the cutoff. It just has never been this extreme. And what this is essentially referring to, and why the sample's chi-square score is so extreme, is a straightforward consequence of the fact that as the sample size increases in a chi-square problem, the sample chi-square score will increase even if you sort of keep the proportion of the 2 categories the same. And we'll see an example of this in just a second. And just a reminder, when we reject the null hypothesis for a chi-square problem, the interpretation that you would sort of explain to someone without any knowledge of statistics is that the observations are very surprising in light of the expectations we have. So in light of the expectation that there would be an equal number of male and female characters represented on serial boxes, the actual observations, where you had 996 male characters and 390 female characters, is very, very surprising. So there's a step-by-step procedure for the hypothesis test of the chi-square goodness of fit statistic. So this kind of chi-square test, where you have just one variable, this is called a chi-square goodness of fit test. There's another kind of chi-square test that we'll touch on, but the goodness of fit test is a very, very common one. And I won't make you go through every single step of the hypothesis testing procedure, but I do want you to be able to sort of understand the logic behind it and how fundamentally, just like all the statistical tests we've looked at so far, it's a way of kind of understanding how surprising your data is in light of your expectations about what the data would look like in some sort of ideal world. Like before, we had like a null hypothesis where we predicted 0 effect, and that was the thing that we were comparing our data to. Here, it's the expectation of an equal representation of all of the values in your data set. So now that we've done this, let's look at some examples of the chi-square distribution in our Blackboard shared folder. So all of these are going to be available to you in Blackboard in the tab in Blackboard called Datasets. So there are actually several datasets here that are chi-square tests. So let's look up one example of these. Hold on, where's the one I'm looking for? All right, so let's actually look at this one, this assortative mating one. So the assortative mating one, the data set gives you a little bit of a what's called a précis or an explanation of what it's about. So in this data set, it tells you that it consists of data from heterosexual married couples, and there are two variables. One of the variables is the husband's eye color, and the other variable is the wife's eye color. So let's look this up together. So opening up a CSV file, which is that comma separated value file, it's going to show you something that looks like this. So we have, remember, these are data from heterosexual married couples. And what you have are the eye color, the self-reported eye color of the male member of the couple, and the self-reported eye color of the female member of the couple. And this first line is just going to be the variable names. And this is common for the data sets we've seen thus far, where we have the first line as the names of the variables. Remember to keep the variable names as a single sort of like set of characters, like instead of self, just a space female or space male, you always put like an underscore or a hyphen. Because a lot of times JASP and other things get confused by spaces. They think that you mean to sort of go to another column when in fact you don't. So this first case on line 2 is a couple where the man's eye color is blue and the female's eye color is blue. And then down here, there's another couple that has that same characteristics. And if we scroll down, you see that this is a fairly large data set. It goes down to line 205. And since the first line was just the names of the variables, we know that we have 204 married couples. And we have like examples of couples that have the same eye color, so green and green, but then we have ones that have different eye colors, green and brown. So in order to open this up in JASP, I would recommend simply downloading that CSV file, and be sure when you download the CSV file not to sort of add anything else to it or modify it. Once you're in JASP, we're going to want to open up this kind of file by going to Computer, go to wherever you have your files. We just downloaded this one called Assortative Mating Chi-Square. And ta-da, we have our data ready for us to look at. So a cool thing about JASP is if you can't see the data well enough, if you just hold the control key and click either plus or minus, it sort of zooms in or zooms out. So the first thing that I want you guys to focus on whenever you upload data, this is something that some of you are a bit confused about with the homework, make sure that the JASP assigns each variable the correct variable type. So for both of our two variables, male and female, these are what kind of variable? Scale variable, ordinal variable, or nominal type variable. So in this case, they're nominal variables because nominal variables are things like categories, and eye color is a great example of a category. It's not scale or ordinal because it's not a number. There's no sort of like sense in which blue should come before brown, should come before green in terms of eye color. And this same logic also dictates that the female eye color should be the same. So the question goes, how would we conduct a chi-square goodness of fit test using JASP? So what we're going to do is we're going to go to frequencies, and we're going to go to binomial test under the classical frequencies tab. So binomial test, so binomial, bi for two, nomial for categories, so binomial, two nominal variables, and that sounds like the kind of test we're doing. So I mentioned before that there's the chi-square goodness of fit test, and then there's other kinds of chi-square tests where we can actually have two variables and see whether the combination of factors fits with our expectations or not. But first, let's just look at male eye color to get, to get what we expect. So we have the male eye color. So like before, there are 204 samples. We know that there are 204 married couples. There's one man in each of the married couples. So you should have 204 scores for eye color. And what you see here is that the majority of the males in this study that looked at heterosexual married couples had blue as the eye color. Then slightly less than 54 had brown eye color, and 36 had green eye color. If you add these all up, they'll total to 204. And JASP is also quite useful because if you don't want to sort of go through the whole list of 204 cases, or sometimes data sets have even more than that, it can just tell you in this table how many eye colors there were in the study. You know that there were 3 values, blue, brown, and green. It tells you the counts for each, and it also tells you the proportion of each of the eye colors compared to the total. So 114, which is the number for blue, represents about 55.9% of the data. And so when it says proportion in this column, 0.559 is 55.9%. So what we have next is a aspect of this column where it gives a p-value. And a p-value is something that we've previously tested before. And you see that blue has a p-value predicted at 0.107. And brown and green have p-values of less than 0.001. So why is it that blue, that eye color blue, has a probability value of 0.107, not significant, and brown and green have values that are significant? One thing to note is that this test is actually testing each of the individual levels of the variable, which is to say each of the values in the data set, against a proportion of 0.5. So this p-value here represents what you would expect if the p-value, it's testing against the prediction that 50% of the total should have blue as the eye color. This is testing against 50% should have brown. And what this leads us to is that if you have the assumption that 50% of the subjects are going to have blue eye color, it is not very surprising that about 114 out of 204 subjects has blue as the eye color. And because it's not very surprising, the p-value is not significant, and nowhere close to being significant. But if you expect 50% brown, you end up with a very, very unexpected finding if you assume 50% of the subjects will have brown eye color, and that's why you have a p-value that is less than 0.001. However, this is not the best way to do this problem. And one of the reasons why it's not the best way to do the problem is because you're doing 3 different statistical tests where what you would actually want to do is one statistical test that tests the general surprisingness of the findings. So let me open up. Just give me a moment. So I'm just going to unshare my screen for just a moment because I just want to make sure that I am showing you the correct thing in JASP. So just a moment, guys. I don't want to give you a tutorial that I sort of mess up at first. So I'm pretty sure I know how to do the chi-square test I want to do. I just want to make sure by using an example I've already done successfully. Go. Lovely. All right, so I'm going to share my screen with you guys. Once again. So I was doing correct. I just got a little bit nervous that I was messing that up. But so the problem with the binomial test here is that our variable has more than two categories. So what we're instead going to do is the multinomial test. And let's once again do it for males first. So the multinomial test is going to be testing a variable in your study that has more than two values to it. So because there's more than two values to the variable of male eye color, it was inappropriate to do the binomial test because the binomial test assumes that there's going to be 50% of each of the category, or only two categories. But because we had three, it makes it very, very difficult to test. But we're going to go back to this in just a second. But the multinomial test is basically what we would get if we followed the hypothesis testing procedure and we tried to calculate the chi-square test statistic using the sort of tabular format we saw in the lecture slides, where you calculate the expected value, you look at the observed values, and then you figure out the expected frequencies, that the squared differences represent divided by the expected frequency, and what you would get is a chi-squared value of 49.059. This is a value that we could sort of determine using Excel or by hand, but assuming that you have set up your your spreadsheet correctly and imported the files, see that there's 2 degrees of freedom. So remember that the degrees of freedom for the chi-square test are the number of categories minus 1. So in this case, there are 3 categories. Male eye color includes blue, brown, and green. 1, 2, 3. 3 minus 1 is 2. And what we would find is that for a chi-square distribution with 2 degrees of freedom and a chi-square test statistic of 49, just about, that is significant. And so the p-value is less than 0.001, which no matter if we had chosen an alpha value of 0.05 or 0.01, that would cause us to reject the null hypothesis. So what we have here is an illustration of the fact that if we were to assume that there should be an equal representation of blue eyes, brown eyes, and green eyes in the category of men in this sample, the actual observations where almost all of the men, more than half had blue eyes, and then fewer had brown eyes and even fewer had green eyes, that is very surprising if you begin with the assumption that the representation of blue, brown, and green eyes in the population is the same. But as many of you know, depending on what part of the world you're from, the difference between the distribution in the population of blue eyes, brown eyes, green eyes is going to be very different depending on where you're living. So, for example, if you're living in a Scandinavian country, there is a pretty high proportion of people with blue eyes. If you're living in sort of East Asia, there's a very high proportion of people with brown eyes. And if you're living in certain parts of Scotland or Northern England, there's a higher than average proportion of people with green eyes. So the fact that if you have a little bit of extra context about what part of the world you're doing the study in, you might predict that you would not expect, rather, to have an equal proportion of all of the different variables. And the variable here is eye color. And this is actually something that you can toggle using JASP. So for example, notice that in the multinomial test, there's an option. The first option, that if the test values that is just already preset, is equal proportions multinomial test. But now, let's go to expected proportions chi-square test. And technically, the multinomial test is also a chi-square test because it's producing a chi-square statistic. But this equal proportions multinomial test is equivalent to saying a chi-square test where each of the values you expect to occur at the same frequency as all of the others. So what we have here is when we click on expected proportions, we have our three different variables, and this thing here, h subscript 0, that should look familiar because that's the null hypothesis. So the null hypothesis is that each of these values has an equal probability. They all have a probability value of 1. And since they totaled 3, you expect 1 out of 3 or 1/3 probability of blue eyes, brown eyes, or green eyes. But what if instead we changed the relative sort of frequencies here so that we expected twice as many people with blue eyes as brown eyes and green eyes? So if we change this value for blue eyes to 2, meaning that we expect twice as many people with blue eyes as with either brown eyes or green eyes, let's see what happens. Oh, so I didn't highlight this well enough, but what we had before was we had a chi-square test statistic of 49 with 2 degrees of freedom, and this was significant, which is to say the data was very surprising if we assume that there's an equal representation of all 3 of our values. But if we go from an expectation of the blue eyes being as frequent as either brown eyes or green eyes to we expect blue eyes to be twice as frequent as either brown eyes or green eyes, let's see what happens. So I'm changing the value of blue from 1 to 2. When I do that, the chi-square test statistic goes from 49 to 6. The degrees of freedom stays the same, and the p-value, oh, this is very funny. The p-value is like exactly on 0.05, which is like a very interesting, like a weird case because do you reject the null hypothesis or not? Technically, if you get a p-value of exactly 0.05, you have to fail to reject the null hypothesis because it's only when p is less than 0.05 rather than less than or equal to 1.5. But let's actually just make this a little bit more obvious by changing the expected proportion of blue eyes to 2.1. And if we do that, the chi-square test statistic shrinks even further. So when it was exactly 2, it was 6, and when we increase the expected proportion of blue to 2.1, it actually shrinks to 5.03. And the p-value now is not significant with an alpha value of 0.05 or 0.01. So you can see that by changing the expected proportions or the expected frequencies of the different values in your data set, that changes what the chi-square test statistic is. So to go back to the cereal box example, what if, let's say you were, this is a kind of a fraud example because the male and female representation is like a politically charged topic, and like representation, you often sort of don't necessarily want the representation of male and female characters to like exactly track like, I don't know, the interests of the people who are consuming the product. You want to sort of like make sure that things are equal for other reasons. Well, let's just say that you assumed that most of the people who purchase cereal boxes and would buy cereal are boys who are interested in sports that are sort of dominated by men, like soccer. If your expectation is that most of the people buying cereal are interested in sports that have like male athletes on them, you wouldn't necessarily expect that the cereal boxes would have an equal representation of male and female characters. You would expect that you would have more male characters portrayed on cereal boxes because the cereal boxes would be advertised to boys who are interested in sports with male athletes, and putting male athletes on the boxes is a way to sell the cereal boxes. It's not clear in this example what proportion you would expect. How many more male characters would be portrayed on the cereal boxes? Would it be like twice as many as the female characters, 5 times as many? But whatever the case, you would not expect an exactly 50-50 split of male and female characters on these cereal boxes. In the case of population characteristics, like the proportion of blue eyes, brown eyes, and green eyes, there often is like a very easy way of like figuring out what the expected proportion should be, which is you can just look at the proportion of different eye color in the population. So for example, you might have like a database of like eye color from people who are from like driver's license data, for example. Like on people's driver's license, it says what eye colors people have. You might be able to get the data sort of scrubbed of people's individual information just to see what the proportion of blue, brown, and green eyes are in the general population or people who have driver's licenses. And let's say you find out in your example that the people who have blue eyes are the most common in the population by about twice as much, a little more than twice as much. And when you have this extra information about the actual distribution of values in the population, you should always use those instead of just an assumption about all of the values should be equally represented. Because in reality, when you have a nominal type variable and there's diversity in the population, often one of the variables is the most common. Like I said, if you went to China, for example, you would find that brown eyes are by far the most common eye color because it's a very homogeneous population and the native population of China is predominantly brown eye color. You'd expect a very, very small proportion of people with blue or green eyes. So this is just something that's very, very useful, and it's something that you should always try to factor in when you're doing this kind of test, or when you see this kind of test done in actual research. Because if you wanted to just get a highly significant finding, you could have just said that for the sake of the statistical test, I'm assuming an equal proportion of blue, brown, and green eyes in the population, and wow, you have a statistically significant finding. But it's the kind of statistically significant finding that is completely it's useless to you because you're sort of assuming something that is pretty likely to be untrue, which is that an equal proportion of people in the population have blue eyes versus brown eyes versus green eyes. And this is actually the same criticism that you read about in some of the earlier readings in the class, in those homework assignments, about the null hypothesis, and how the null hypothesis, which predicts no effect, is often a bad starting place for the sake of trying to understand whether a treatment or intervention is actually having an effect. Because in the case of, in one example, there was an article, this was a Box article by Brian Resnick that talked about how when you're giving antidepressants to patients with depression, one of the things that you expect, that's just clinically expected, is patients to sort of just get better over time, even not accounting for any treatment. This is, I can't recall the effect of this effect at the same time. It's not the placebo effect. Oh, it's called regression to the mean. Because typically when patients sort of show up, or anyone shows up with some kind of sickness or injury, they're typically at their sort of worst state. And in the case of psychological problems, often they seek treatment, patients seek treatment when they're at their worst, and then just gradually, just through no intervention on the cause of the clinician, the person will sort of return to their baseline, which is often less depressed than when they showed up at the clinic. So assuming that the null hypothesis for a study of like an antidepressant drug or a therapy for depressed patients is going to have the assumption that if the null hypothesis is true, there'll be no effect. We know this is not the case because patients tend to just get better over time. And what you should be testing is whether the drug or treatment or therapy that you're testing is better than what you would expect, given that patients tend to return to a less depressed baseline over time. So let's see additional statistics that can be generated with JASP. So JASP can tell you stuff that we saw up here. I encourage you to use multinomial tests to start with. I forgot that we were looking at a database with three different, rather than two different types of values. So once again, you see the observations and the expectations. So the expected values here of 104, 50, and 50, these are actually based on these proportions that we just modified. So if we were to return the expectations to equal proportion of all three eye colors, the observations stay the same because that's just a property of our data. But the expectations are that there should each be 68 observations of blue, brown, and green eyes respectively. But let's go back to our world in which we predict that there's just over twice as many people with blue eyes. And when you do that, the expected frequencies match the observed frequencies better. And I happen to know that this data set was from a Scandinavian country. So in general, whenever you see a data set with like a lot of information about people, it's almost always from some Scandinavian country, because Scandinavian countries have like a very different healthcare system. Like it's a lot more like intensive, and like you're put into a database very early because the government sort of tracks all individuals because they're all part of the same healthcare network essentially. And you end up with like a lot of data because the government is tracking everyone, and then occasionally the government releases the data publicly. So basically, whenever you see a lot of data like this, it's almost always from a Scandinavian data set. And here it's especially funny because the proportion of people with blue eyes really sort of gives away that it's from a Scandinavian data set, because blue eyes are very common in places like Norway and Sweden. And you can also choose to generate a plot So here, it's simply showing you the counts of the 3 different eye colors. Could be useful to you. But if you remember back to what we were interested in this data set, remember we had the cases representing heterosexual couples, and the heterosexual couples have 2 scores for each, the eye color of the man and the eye color of the woman. Oops. So what happens when we add another factor? Hold on a second. Hold on, I know there's a way to do what I want to do. So I'm not going to sort of be, I'm not going to sort of make you sort of look into this, but one of the things that you might see in the future is a kind of, you might see something called a contingency table, which is like the chi-square distribution or the chi-square goodness of fit test, which only uses 1 variable with multiple nominal values, but here we actually have 2. So what you see is a table where you have 1 variable represented by rows, in this case, the male's eye color, blue, brown, and green. And then you have the female's eye color, blue, brown, and green. The females, there were no females who had different eye colors. And what you actually see here is how many cases in your data set have different combinations of the female partner and the male partners having certain combinations of eye color. So each male and female partner can have 1 of 3 different eye colors, and each couple has a unique combination, a unique pair of male eye color and female eye color. So for example, what we see here is that the female partner with blue eyes and a male partner with blue eyes, there are 78 couples in the data set that have this combination of male with blue eyes, female with blue eyes, and so on for the different combinations of female with brown eyes, male with green eyes, female with green eyes, male with blue eyes. And what you see here is a breakdown of the number of blue-eyed females represented at the sum of all of these columns, and then males as the sum in this column. But then the total number in these 9 boxes, which is all of the married couples in every possible pair, is 204, because that was the number of cases we had. And one of the questions that the contingency table, this chi-square test with 2 different variables, is for the combination of the male eye color and female eye color in the couples, is the distribution of these pairs in the center of the contingency table, it's called, what you would expect if it was just randomly sampled blue, brown, and green, and those were randomly sampled and paired with male, blue, brown, and green-eyed men. And you can probably tell that the fact that there's 78 blue-eyed men with blue-eyed women, that's kind of a lot, even given the proportion of people with blue eyes in the whole study. So if you assume that all of these couples are sort of randomly pairing and they don't care, and there's no sort of like selection process or non-random nature of sort of couples with where one partner has one eye color, sorting with a couple with another partner with a different eye color, it seems like there is some kind of selection effect. And the fact that the distribution of these pairs is not random is something that is encoded in this chi-square test. This is not something I'm going to test you on. I just want you to know that there is a way to kind of test pairs of values. And once again, there's a chi-square test statistic. Here it's 33. It has an n of 204, so there are 204 pairs. Here, there's 4 degrees of freedom. The 4 degrees of freedom here, it's not too important to know, but it's actually the number of degrees of freedom for female eye color and male eye color, so 3 minus 1 plus 3 minus 1. And the chi-square test statistic that says it's 33. This is statistically significant for 4 degrees of freedom. And when you do this kind of study, where you're looking at the probability that certain pairs will sort together, when you get a significant value of chi-squared, what that is telling you is that there is at least one combination of eye color in heterosexual married couples that is different than what you would expect if it was totally random what eye color the male partner has versus what the female had. And this actually can bring me into some psychology here. It turns out that people are more attracted to people who, well, it was previously thought that people were more attracted to those who had the same eye color that they did. So if you had blue eyes, you might be more attracted to someone who also has blue eyes. But it seems in recent years, when more study has been done, what's more important than what color eyes you have is what color eyes your mother had. And the thought is, if when you're a baby, you sort of imprint on your mother and you look into your mother's eyes a lot, and your mother sort of becomes the model of the sort of person you want to date later in your life. So even if you're a woman, whatever your mother's eye color is, you will find that eye color more attractive. So it's an interesting example of how early in life experiences, in this case, looking at your mother's eyes, can really sort of influence the kind of romantic decisions we make later in our lives. So like I said, I wanted to quickly go over some just examples of independent samples t-tests and then of correlation type data sets. None of them on the exam and in the homework assignment are going to be with like 200, and they'll only be with the sort of goodness of fit style chi-squared. So don't worry if this assignment with, excuse me, this example with 204 subjects was a bit complex. So let's look at the data set that's really good for independent samples t-test. All right, this one is a diet study. Computer freaked out. All right, so yeah, like this is a fairly large study. Yeah, I should have tried downloading this. There it is. All right, here we go. So this is a very large data set, and it was from a study. This is actually just a selection from a very large data set. And the goal of this study was to see whether a particular diet would affect somebody's weight. And they also looked at some other factors as well to see whether those other variables, such as the person's age and the person's gender or the person's height, also predicted what their weight would be. So you have person, and this person here, this is just the case number. So one of the things I liked about this data set is that the case numbers are actually out of order. So you see 25 and 26 are up here. And this is actually fairly common. So what you see here is something that I've mentioned before, but I don't think I've ever pointed out in the context of an example. Notice how for subjects 25 and 26, sorry, I should zoom in. For subjects 25 and 26, they don't have any gender information in the gender column. And what we called these were missing cases. So missing cases refer to cases, so lines or rows in a spreadsheet, where one or more, hold on, we have a question from the chat. Okay, Denise, how about now? Is everything okay? All right, can you guys hear me a little better?
Yes.
Awesome. I turned off my video and I restarted Excel just because I thought that might be the issue. But also I stopped sharing my personal video, but probably most of you aren't looking at that anyway. All right, so can you guys see the screen that I'm sharing? Is Excel still visible on the screen? All right, that's great. So what we have here, thank you, Amanda. So this is an example of a missing case. Almost every large data set that you try to compile is going to have missing cases, where just for some reason, sometimes you either fail to collect or your subject failed to disclose a variable that you would otherwise want to know. So there's an open question about what actually qualifies as a missing case. There's some kind of, like, for example, if you have this sort of study where the only variable missing for these subjects, 25 and 26, is their genders. If you are doing some analysis where you don't care about gender, it doesn't matter that these subjects are missing that case. But if you're doing an analysis where gender is important, or you plan to sort of do a large analysis and then do a breakdown by gender, it's not good that if you do one analysis where these two cases are included because gender wasn't a part of the analysis, but then for the sake of a breakdown by gender, you have to exclude these. because these are still part of your data. It's just that for reasons outside of your control, or because you were careless or whatever, those particular variables are missing. So there's often going to be some kind of criteria for if you have a missing case, like in this case, if you have the gender variable missing, do you include them in the analysis, yes or no? And you would typically see this specified in the method section of a paper. So what you see here is, for the sake of us, what we're going to be looking at are these three columns. I think we've looked at this data set before, but I wanted to go over it once again. So we have the person's weight before they went on one of three diets. And we have their weight 6 weeks after going on that diet. So this is a CSV file. And for the CSV file, let's open it up. So I'm actually going to skip this just because we don't have all that much time left. And I know that I've gone over this independent samples t-test problem. So what I'm going to do is I'm going to, when I post this video tonight, I am going to post I'm going to sort of refer back to the video timestamp when I talk about this diet example, so you can see how to do an independent samples t-test problem. But let's actually open another type of data set. This type of data set being one that involves correlation and prediction. So correlation and prediction. This is a simple one that hopefully doesn't hit too close to home. If you come from a family that has a lot of issues with alcohol and overdoing alcohol, like mine, it's no fun to think about alcohol, but this is an interesting study because it refers to real-world information about the relationship between how many alcoholic drinks we consume and this number called blood alcohol concentration. So blood alcohol concentration is literally what percent of your blood is alcohol, or ethanol, the molecule in alcohol that sort of makes you drunk. And here you have 16 students, and you have the number of beers that they consumed, and then you have the blood alcohol concentration of each student, which you want to know the relationship between the number of beers drank and the blood alcohol concentration of the students. I mean, for like most of you know that it's pretty straightforward, the relationship between your blood alcohol level and the number of alcoholic drinks you consumed. But let's actually look at it using the correlation and prediction math we've previously used. So the first thing we're going to do when we open something up is we are going to inspect what variables JASP assigned, so what variable types JASP assigned to each of the variables we had. So the first thing you notice is that there's a variable here called student. And student is actually, we're not going to be analyzing this because this was just basically labels that were given to each of the students in the study. You could have omitted this entirely and it would have been fine. But for the record, these numbers this is a nominal type variable, even though they're numbers, because they're just being used as labels to identify the students. There's no sense in which there's an order to them. It's not like the first student, you expect something different than the last student in the list. And they're not scale type variables because even though they're numbers, there's no like ratio to them. There's no like relationship between knowing a student has a value of 5, they're the 5th student in the list or whatever. It doesn't tell you anything about what they are in relation to the 10th student, even though 5 is 1/2 of 10. So the number of beers, this is actually a scale type variable. It is scale type variable, it is a ratio scale type specifically, because the difference between 2 beers and 4 beers is 2 beers is 1/2 of 4, and there is a 0 point on the scale of number of beers consumed, which is 0 beers. And similarly, blood alcohol concentration is a scale type variable. It's just a number, it's a ratio. It's always going to be less than 1, because if it is exactly 1, that means you have 100% of your blood is alcohol, which you're in big trouble. And this should look very, very familiar, because whenever we're doing a correlation style problem, trying to find like the regression line and trying to find the regression equation that those A and B values that we'll just look at, we'll always be dealing with 2 variables that are both numeric. So just like before, we're going to be looking at regression. There are 2 different options here. So the correlation option is the more basic one, but linear regression one is the one that's going to give us the things we care about, which are the A and the B. But let's go through them one at a time. The correlation one is useful simply because it actually gives you an option to sort of plot your data, which is something that you'll always want to do. So here we have the blood alcohol concentration and beers as 2 different variables. We'll choose Pearson's R, which is just the correlation coefficient. And you can just follow along with what I do here. So it's going to give you the variables presented like this, where blood alcohol concentration in beers is kind of confusing how it shows it here, but essentially, let me just move this to the side. Hold on, JASP is being banned. All right, here we go. So it's a bit confusing how it presents it up here. It doesn't want to JASP does not want to sort of show you the same data twice to make you think that you have 2 different values that are just both the same. So it instead sort of looks at the 2 variables, and when it gets the second variable, then it starts listing the sample size, which was 16 students. It gives us our Pearson's R, which in this case is 0.894. So 0.894, if you recall back to the times where we were looking at the strength of correlations, an R of 0.894 is very close to the theoretical, perfectly strong correlation, the positive correlation of R equals 1, where there is a perfect correlation between the X variable and the Y variable. And what you see here for beers versus blood alcohol concentration, it's sort of wonky how it's being presented here. So what you have here is beers represented on the x-axis. I don't know why it's doing this in a weird way. In any case, beers is on the x-axis because it's the independent variable, and blood alcohol concentration is on the y-axis, which is the dependent variable. When I post this, I'm going to highlight how it is you can get this to show the correlation plot in a way that it's not, it doesn't have just words all over the place. But now to figure out the characteristics of the regression line, the characteristic of the regression line you see here, we're going to go to regression, linear regression. Here we need to utilize our knowledge that blood alcohol concentration is our dependent variable because it depends on the number of beers the students drank. As a covariate, which is just a fancy word for the independent variables in this experiment, we're going to put beers. One of the things that some people were confused about for the correlation and prediction homework is that JASP automatically assigned some variable as a ordinal type variable, and it wouldn't let you add it as a covariate. So JASP wants everything to be in numeric variable terms. And it actually shows you the little ruler icon in the bottom right to indicate this covariates box will only accept scale type variables. So as soon as you add these to your linear regression model, it immediately gives you a couple of things. Notice that H1, first of all, you have a null hypothesis that predicts this uppercase R is just basically when you have only two variables, it's the same as lowercase r, the Pearson's R. And remember, when we're testing a correlation coefficient, it's always going to be testing against the null hypothesis that there is no correlation between the two variables. But our data, which is in this case, the research hypothesis, is that our data has the correlation coefficient of sort of the two variables if you computed their correlation. So 8.894, which is what we saw above. Ignore this stuff here. This is a model of the analysis of variance, which we did not get to in the class. But let me just quickly add the statistics down here so we can see what we care about. We don't have to do this, but it's always useful to see the descriptive statistics, so just click them there. Let's generate a plot. So when I said that I prefer using the correlation option from the regression thing, it just produces a simple plot showing the relationship between the x and the y variable. Because the linear regression option in JASP is more complex, it gives you multiple options. But in terms of figuring out the regression line, which had two terms that you didn't know, which was an A term, which represented the slope of the regression line. That slope of the regression line is given by this number, 0.018, and the value of b in the regression equation, which is the y-intercept, in this case called the intercept, is given by minus 0.013. So these are your values of a and b, which you need to know, for instance, for the homework, where you have to figure out what the regression equation is for a small data set that looks sort of like what we just did. And so because you know the values, you're trying to find the value of y, which is the predicted the predicted dependent variable, otherwise called the criterion variable, from a value of x called the predictor variable. Because the equation for the y variable requires you to know the value of x, which you're given in the problem, the value of a, which you find down here, 0.018, and the value of b, which for this problem would be minus 0.013, you can use those three terms to predict what the predicted y-score would be for a given value of x. So in addition to this, that I'll post on YouTube right now because the class is over, I'm also going to post the presentation I gave last semester where I go through the same things again. So if you want to see another tutorial, I gave the same assignment last semester, and I probably did a bit better job explaining things. I will highlight which is the best explanation for the sake of following along with the tutorial. So I'm going to unshare my screen. And that concludes not just today's class, but the class as a whole. Thanks everyone for sticking around. Feel free to contact me in the future if you have any questions. Talk to you soon.